Physics 2212 Magnetic Field of a Bohr Magnet by Swayam Sanketkumar Trivedi. Introduction. Purpose. The purpose of this lab is to experimentally investigate how the magnetic field of a Bohr magnet varies with distance and to compare the measured results with theoretical predictions for both on-axis and off-axis magnetic dipole fields. The fundamental physics principles used include Biot-Savart's law, which states that a small segment of electric current creates a magnetic field at a specific point in space. The second is magnetic field of a dipole. So the magnetic dipole generates a magnetic field similar to a tiny Bohr magnet resulting from the looped motion of electric current. And the third is distance dependence formula, which relates the strength of a magnetic field from a Bohr magnet decreases rapidly with distance, typically followed by following an inverse cube relation. So the preview of the main results are that n was equals to minus 2.998 and the magnetic dipole moment was 4.613 A times m squared. The main physics ideas used throughout this experiment include Biot-Savart's law for a moving charge, the magnetic field of a dipole, the power law distance dependence, and the logarithmic linearization of power law. In the experiment, the system was the Bohr magnet and the magnometer. The surrounding was everything else. The experimental procedure first included orientating the phone so that the magnometer is perpendicular to Earth's magnetic field as shown. The second was determine the exact location of the magnometer chip on the phone. And the third was measure the distance between the magnometer and the Bohr magnet in both on-axis and off-axis configurations. On the left, we have the distance measurements for different magnetic field strands, and the graph shows the average linearization of the averages. Based upon the distance dependence formula and the equation of the line of best fit, we can find n and k. Through the linearization of the graph, we were able to get the values of n and k. And through this, we were able to find the magnetic dipole moment, which turned out to be 4.613. I now did the same thing, but for the off-axis. The only difference was that I moved the magnetometer up in perpendicular to the direction of the axis, and the result of the average is given in the table. We now move into the computational model part of this experiment, and in this we set the initial conditions where we changed the value to what we had previously gotten in the theoretical part of it. This was the visual results I obtained, where this was the on-axis, this was the off-axis, and this was the 45 degrees that I had set. Some assumptions and errors could have been made throughout the experiment. The first assumption was that the Bohr magnet is modeled as an ideal magnetic dipole with a uniform magnetic moment. The second was the magnetic field decreases with distance according to the inverse cubic law expected for a dipole. Some errors may include nearby electronic or magnetic materials introduced interference, which distorted the magnometer readings. And the second is uncertainty in locating the magnometer sensor within the phone led to inaccuracies in distance measurements. Some of the questions and observations were, when the magnometer is far away from the magnet, it measures a near zero magnitude field in the x direction. This was true. As the magnometer moves closer to the magnet, the measured x component of the magnetic field decreases, which was false. The position of the magnometer has no effect in the measured x component of the magnetic field, which was also false. And the fourth one, as the magnometer moves closer to the magnet, the measured x component of the magnetic field increases, which was true. What if? What would happen if we didn't align the meter stick with magnetic north and instead placed it in an arbitrary angle relative to Earth's magnetic field? So the misalignment would cause the Earth's magnetic field to interfere with the magnet's field, making it difficult to isolate the Bohr magnet's contribution. This overlap would skew the magnometer readings and compromise data accuracy. Second, how the results change if we use two identical Bohr magnets placed end to end in the same direction. Attaching two identical magnets in series would effectively double the magnetic moment, result in a magnetic field with twice the magnitude. The direction of the field, however, would remain the same. Thank you.